So we are doing LOL charts. LOL charts to talk about energy transfer into or out of a system. So we have to understand what the system is first. Now, one of my best and brightest, Kelsey, she just said when we're talking about this first one, a cup of hot coffee cools as it sits on the table. So what is really happening? And she said the coffee is warming the table. So we have to identify the system. If we're focusing on the table being warmed by the coffee, which we could do in this case, then the table would be the system. But as we read it, a cup of hot coffee cools as it sits on the table. So what are we really going to think of as the system? The coffee. All right, so in the first step, what you do on this LOL chart is you're going to write in this bubble and leave a little room, but you're going to write what the system is. So in this case, coffee with two E's, not one. All right. Okay, coffee cools as it sits on the table. All right, now we have this shape like an L on the left side. It's really going to be a chart. And we have some E's along there, and these should become familiar now that we just went over those notes. We have ETH, that stands for what? Thermal energy, okay? So thermal energy we think of as what? Temperature, okay? So we think of that like temperature changing, and I just said a minute ago before I started recording, but there's two things we really need to focus on with these LOL charts. One is temperature, and what was the other one I said? Do you remember? Phase, okay? We see that with the EPH, energy phase, or phase energy, okay? And then we have ECH, what's that for? Chemical energy, right? We're not going to deal with that too much. We're going to deal mainly with the first two. What we're going to be doing is putting in blocks for these things, all right? And we have to think about it a little bit. So we have an initial on the left over here. So this is where we're going to put our initial situation. And then we have our final over on the right. What's our final situation going to be like? Okay. So now here's one thing you just have to know in order to do these, is when we do the different phases, solid, and this is always going to be true when we do these, solid is going to be one block. Okay? If we do a liquid is going to be two blocks. And if we do a gas, we're going to jump up to 4 blocks. Okay? Now, if we think about that, it makes sense because we do know that when things are in the solid phase, they have less energy because when we add energy to them, then they become liquids, right? And if we add energy to liquids, then they become gases, okay? We go to 4 blocks and skip 3 because to show that gases have much more energy. And when we talk about the interactions that happen between particles, which I was mentioning earlier, and solids with the particles so close together, there's really strong interactions between the particles. In liquids, they're a little more spaced out. The fact that they're a little more spaced out means that those attractions between particles aren't as strong. There are still attractions between particles, but they're not as strong. Gases are really spread out to the point that the forces in between them are very, very, very weak. All right? So that's what we're going to do for phase. So in this situation in number 1, is there any kind of phase change? A cup of hot coffee cools as it sits on the table. So does the coffee change phase? Okay? It doesn't say anything about the coffee cooling to the point where it freezes or anything like that. So this is what I'm going to do. I'm going to show that coffee at the beginning is a liquid and at the end is still a liquid. And a liquid is 2 blocks. So we're talking about the phase energy. So under phase energy, I am going to draw 2 blocks. Okay? And at the end, I am going to draw 2 blocks. These lines are just kind of in there to help guide you. All right, you don't even really need them. All right, so that's the first thing we're going to do. Now, the thermal energy is going to depend on whatever you want it to do. It's going to be different, but this is where we have to think about it a little bit. Okay? Would it make sense in the initial to put maybe 1 block for thermal energy? Okay? Could I? I guess I could. I don't really want to, though, because I want to show more because it's going to be cooling. Maybe I'll do for thermal energy, I'll do like 3 blocks because it was pretty warm. Okay, it was hot coffee. These lines are terrible. My apologies. Okay, so I'm going to do 3 blocks there. I could have done 4. I could have done 2. I could have even done 1, I guess. All right, so then it's going to cool down. So what's a thermal energy at the end going to be like? You said 2? Okay. Well, this is another point, too. So we could use this as a norm. I was watching a video on these LOL charts, and there was this guy that said he likes to establish with his students room temperature being 2 blocks for thermal. So that's the energy thermal. Should we do that too? So if we say something cools to room temperature or warms to room temperature being 2 blocks, I probably should have made that first one bigger then. Would you guys have a problem if I changed the thermal energy in the first one to 4 blocks? Can we do it, or would it mess you up? All we gotta do is just add another box, right? I'm sorry, guys. I know. I should have been more prepared. Just made you guys write a whole nother block up there. All right, so if it cools to room temperature, and we just established that we're going to have room temperature be 2 blocks. So something like this. All right. So now in the initial diagram on the left, how many total blocks do I have? Okay, so we've got 6 blocks over here. And how many do I have at the end? Only 4 blocks. Okay, so thinking in terms of the system and knowing conservation of energy, we know that that energy, that difference of 6 to 4, can't just disappear. Because conservation of energy means that energy cannot be created or destroyed. It can be transferred into or out of a system, but it cannot be created or destroyed. Okay, you should know that for a quiz, like maybe Tuesday. All right. So what happened to it? Where'd the other 2 blocks go? Jacob? What's that? Chemical energy? Is that possible? Good thinking. All right, maybe it goes in the last category. All right, but if we think about the coffee just sitting there, is it chemically changing as it cools? So think about this. In order for the coffee to chemically change, it would have to change into a different substance. Okay, so that's not it. Good try, good try. So where's that energy going? Maybe to the table. Maybe to the cup. Maybe to the air. What do we call all those things? We were just talking about a little while ago. We have the system, and then we have the what's around us. The surroundings, it's called. Okay? The surroundings. So what we do with this bubble, what's left here, is we're going to show that 2 more blocks had to go in or go out of the system. Go out. Okay? So what I'm going to do here, it's a little trickier. I got to be a little bit artistic. But I'm going to show 2 blocks like this. And I'm going to put a little kind of arrowhead on it to show that it's leaving the coffee. Okay? And I could even make a little note of that. 2 blocks leave. Okay? If we want to think of this process, we can talk in terms of endothermic and exothermic. Have you ever heard of those words before? Okay? Never have? So exothermic and endothermic are ways of describing heat change in a system. If heat is released by the system, if heat leaves the system, if this classroom is the system and we want to leave, we would go out the exit, right? Exit takes you out. Is that what we do? Okay? So leaving we call exothermic. Okay? So the system is releasing energy. Energy is going out. And then if energy were to be going in, we call that endo. So I think of it as if we're leaving, we're going out the exit. If we're going in, then we're going in the dough. Endothermic. All right? That's how we do these charts. It's confusing, is it? It's different, that's for sure. But we're going to practice some more of these, and I want you to try to do them on your own to see how you do. Okay? So you want me to just kind of run through the steps again? Do one more, you think? I'll tell you what, I'll give you a few minutes to try to do it on your own, and then we'll go over it together. All right?